Rules for exponents. First, we want to look at what exponential form looks like. We have a base and an exponent. The exponent is a superscript number, so it's a little smaller and a little higher than the base. What that means in expanded form is that the base is multiplying itself 5 times. So this is really a little tally to tell you how many times the base is multiplying itself. So let's go ahead and use that knowledge to evaluate these expressions. Evaluate means that we're going to get rid of all of the parentheses and the exponents, multiplication, division, addition, and subtraction that we can so that the expression is as simple as it can be. So 8 squared means 8 times 8. It's the base multiplying itself twice, and 8 times 8 is 64. Here we have a negative 3 to the 4th power. So that means negative 3 multiplying itself 4 times. So a negative times a negative times a negative times a negative, we're going to have an even number of negatives. We recall that that means we're going to have a positive result. 3 times 3 is 9, times 3 is 27, times another 3 is a positive 81. This looks very similar to example 2, but notice that the exponent of 4 is only on the 3. It does not affect the negative in front. So this really means the opposite of 3 times 3 times 3 times 3. It's only the 3 that is multiplying itself 4 times, and the negative is sitting out there in front waiting to be used. Now we have just one negative sign, so our result will end up as negative. 3 times 3 times 3 times 3 is 81. So we have a negative 81. This is a common mistake that even my trigonometry pre-calculus students will make. So make sure that you take note of this and remember that when you have parentheses around the entire negative 3, it's the negative 3 that is multiplying itself 4 times, whereas in this one, the 4 only belongs to the 3. It's only the 3 that is multiplying itself 4 times. The negative is sitting out front waiting to be used there at the end. Now consider these examples. Can you draw a conclusion from looking at these examples? Here I have 2 cubed times 2 to the 4th. So this is 2 times 2 times 2 times 2 times 2 times 2 times 2. Now, rather than going ahead and actually evaluating what this is, can you write this again in exponential form? Well, I have the same base in both of those parts. I have 3 2's here and I have 4 2's here. Wouldn't that mean that I have 2 to the 7th? So this would be a way for you to write that in exponential form. Now 2 to the 7th is 128. If we wanted to evaluate it so that it's not in exponential form, we would put 128. How do you do that on the calculator? Let's grab our calculator here. So we have a 2 exponent of 7. Enter, we get 128. For the next example, I have 3 to the 5th times 3 squared. Now, I don't want to do this the same way that I did this. I don't want to have to write 3 out 5 times and then 3 again twice. Can you figure out a quicker way to do this? In other words, is there a way to go from this part to this part quickly? Well, it looks like we have 3 2's here and 4 2's here, so altogether we have 7 2's. We're really just adding the exponents if we're multiplying numbers of the same base. So I have 3 to the 5 plus 2 is 7. So let's try that on the calculator. 3 to the 7th power is 2,187. Okay. And think about how handy this would be if we had very large exponents, like 2 to the 19th times 2 to the 87. You would not want to write 2 multiplying itself 19 times and then another 287 times multiplying itself and then count those up. So we go ahead and start using our little shortcut that we made. This is actually called the product rule for exponents. So if we have an x to the m times x to the n, that's the same as x to the m plus n. You need to note that the base must be the same. You can't use this if the bases that you're multiplying are different. So here I have 3 times 3 squared. Now, there is an exponent here. We don't write it, but it is there. It's an exponent of 1. If it helps you at first to write that in, then go ahead and do that. 3 to the 1 times 3 squared is 3 cubed. 3 cubed is going to be 27. X cubed times x to the 6th, that's x to the 9th. We can't evaluate that anymore, so we're finished at that step. Here I have 4x squared times 5x to the 5th. Now remember what I said about the bases needing to be the same? It would help here if we can identify what the base actually is. Here the base is x. 4 has nothing to do with that base because the exponent is only sitting on the x. We know that because there are not parentheses around that entire expression. If there were, we'd have a lot more difficulty with this problem. So here we really only have the exponential expression is x squared. The same with this part, x to the 5th. In fact, if we wanted to, we could rearrange this. This is multiplying 4 times x squared times 5 times x to the 5th. Since multiplication is commutative, I can rearrange this so that I have my constants in front and my exponential expression second. Now it might be a little easier to see what's going on here. I have 4 times 5 is 20, and x squared times x to the 5th is x to the 7th. That's a much simpler expression than what we started with. In our fourth example, I have 2 exponential expressions in these parentheses, and they're being multiplied together. So we can rearrange this if we wanted to, similar to this, or you can just think about it. Let's go ahead and explicitly write it out like we did in the problem before. The 3 is just hanging out in front. We haven't used him yet, but we do have to carry him along until he gets used. Then I have a negative x times x squared. I'll put those together. And a y cubed times y. You notice I put the negative there and it doesn't get here. So make sure that you only have it one place. Don't generate another negative sign. So first off, let's take care of signs. I have a positive times a positive is going to be negative overall. 3 is the only constant that I have multiplying, so we're going to have a negative 3. Right, now we have an x times x squared. Remember, we already took care of the negative here, so it's just an x times x squared is x cubed, because remember, this is an x to the 1. Again, over here, this is a y to the 1, so it's y cubed times y to the 1 is y to the 4th. You're adding those exponents if you're multiplying numbers of the same base. Later, you're going to use this type of skill when you're doing geometric problems. So this is a part of one of those problems. We have a shape here. We're going to assume that it's a rectangle, and one side is 2x squared in length, and the other side is 5x squared in length. If we want a simplified expression for the area of the figure, what we need to do is remember the formula for the area of a rectangle. So we have area is length times width. Area is, my length is 5x squared times width is 2x squared. So my area ends up being my constants, 5 times 2, and x squared times x squared is x to the 4th. So a simplified expression for the area of the figure is 10x to the 4th. Let's observe these examples. Can you find a quicker way of simplifying them? So we have x to the 5th divided by x squared. Let's go ahead and write that out in expanded form. This is x times x times x times x times x being divided by x times x. Now, you remember when we have something on top and the same thing on the bottom, that they end up canceling as 1. So x divided by x is 1. X divided by x is 1. We're removing a factor of 1. And we're left with x cubed on the top over 1 on the bottom. So x cubed is our simplified answer. Now, when we get to this example, I sure don't want to write out y multiplying itself 10 times divided by y multiplying itself 3 times. So is there a quicker way? In other words, can we get from here to here quickly? Well, if you recall with the multiplication, you're multiplying numbers of the same base, you end up adding the exponents. Here we're dividing numbers of the same base, so it only makes sense that we would subtract. In fact, we subtract the bottom number from the top number in the exponents. So we could write this, instead of this way, we could write it as x to the 5th minus 2. So x to the 5 minus 2, which becomes x cubed. Let's apply that here. That'd be y to the 10 minus the exponent on the bottom. So y to the 7th. A lot quicker than writing it all out in expanded form. This is actually the quotient rule for exponents. So if we have the same base on top and bottom, and those numbers have exponents, then we can write the base with the top exponent minus the bottom exponent. So let's go ahead and use that property here. 8 to the 12th divided by 8 to the 4th. Well, that's 8 to the 12 minus 4, which is 8 to the 8th. Now 8 to the 8th, let's pull our calculator over here. 8 to the 8th is a rather large number. Generally in my lectures, I say that if the number after applying the exponent is larger than a zip code, then we can just keep it in exponential form. It's a little easier to work with. Certainly if you needed to have the number in its expanded form, you could do that, but we're just going to keep it here in the exponential form. The same thing here. I have r to the 8th, s to the 9th over rs. So that would give me an r to the 8 minus 1. Remember, r has an exponent of 1 down here. S to the 9 minus 1. Again, there's an exponent of 1 on the s. These are being multiplied just as they're being multiplied here. So we have r to the 7th, s to the 8th. Here I have b's on the top and b's on the bottom, and I can go ahead and put the b's together on the top and the bottom and then do my quotient rule. So we're going to use the multiplication rule first that we learned before, quotient rule. Well, let's see, this is going to be b to the 4 plus 5 is 9 over b to the 2 plus 3 is 5. And that is going to be b to the 9 minus 5 is 4. So made quick work out of that. Same with over here. We have h to the 3 times h to the 6 times h to the 1. Go ahead and write that in explicitly if you need to. So this is an h to the 10th over h to the 9th. And that gives us an h to the 10 minus 9 is 1. Now, as an answer form, I'm not going to write an exponent of 1. We want it to look nice and neat as possible. So we'll just leave it as an h. Now look at this example. Is there another way to write it or think about it? I have a to the 5th times a to the 5th. Remember, I have this base. We're looking at a to the 5th as the base squared. So a to the 5th is multiplying itself twice. Now I already know that a to the 5th times a to the 5th means a to the 5 plus 5. So we end up with a to the 10th. Is there another way to think about this? Remember, we want to get there as quickly as possible. The fewer steps that we can do, the more elegant the problem can become, and the simpler it is, we won't make as many mistakes. So is there a way to get from here to here quickly? Sure. We have a to the 5th all squared. So we have an exponent already, and it's being raised to another exponent, so we can just multiply the exponents. This is called the power rule for exponents. So if I have some exponential expression and it's raised to another exponent, then it's that base to the exponents being multiplied together, or x to the mn. So if I have 2 cubed all squared, we can say that this is 2 to the 3 times 2 is 6, and we can do 2 to the 6th on the calculator quickly. 64. Here I have my z cubed all squared. So we'll do this in a couple of chunks here. Z cubed squared is z to the 3 times 2 is 6 times 5 z to the 5th. Remember, this exponent of 5 has nothing to do with this number. It's only sitting on the z. So I have a 5. Now, when I'm multiplying numbers of the same base, you end up adding the exponents. So z to the 11th. 5z to the 11th. I want you to compare these examples. Is there a difference? Here I have b squared times b cubed Remember that is b times b times b times b times b. So how many times do I have a b multiplying itself? 5 times. Here I have b squared cubed. So that means b squared times b squared times b squared. So if I have 2b's times another 2b's times another 2b's, then that would be b to the 6th. So there is a difference. So you need to set in your mind a way to be able to differentiate between these problems because they'll be all mixed together in a homework assignment or any kind of a problem that you would do. So here we're multiplying numbers of the same base. We add the exponents. Here I already have an exponent and I'm raising it to another exponent. So you raise a power to a power, you're going to multiply the exponents. One way that I kind of visualize doing this is a lot of times parentheses indicate multiplication. So here it's easy to see we have b squared and there's a parenthesis between that exponent and this exponent. So it reminds me, it's kind of a good way to remember, to remind myself, it's kind of a good way to remember that we're multiplying those numbers, not adding them as we did over here. Look at this example. Is there another way to write it and evaluate it? First, let's write it out in expanded form. It's 3 over x times 3 over x times 3 over x times 3 over x. So isn't this the same as 3 to the 4th over x to the 4th, since we multiply fractions straight across? And we put 3 to the 4th in the calculator, and we're going to get an 81. So this is 81 over x to the 4th. Okay, is there another way to write this and evaluate it? Is there a way to skip this part where we have to write it in expanded form? Sure. So what this means is this exponent of 4 is going to everything in the parentheses. So 3 is to the 4th and x is to the 4th. You have to raise both the numerator and the denominator to the 4th power. So we could skip from here straight to here and then evaluate it from there. So now we get an idea of the powers of a product and a quotient. We already did an example like this where we have a product and both things are being raised to the nth power. We also have this quotient where the parentheses indicate that both the numerator and the denominator are being raised to a power. So let's practice on simplifying these expressions. I have here ab to the 3rd power. Both a and b are being multiplied. So it's a cubed both a and b are being raised to the 3rd power. So it's a cubed b cubed. Second example here, everything in the parentheses is being squared. So I have a -3 being squared. That means a -3 times a -3. That gives me a +9. Then I have r to the 4th squared, which is r to the 8th. And a t cubed squared, which is t to the 6th. Remember, when you have an exponent already and you're raising it to another exponent, you multiply those exponents. Here we might need to take a couple of steps here. I have an exponential expression to an exponent, another exponential expression to an exponent, and then we can go ahead and simplify after there. So y cubed squared is y to the 6th. Remember, raising a power to a power, you multiply the exponents. And here I have x to the fourth y all cubed. That means x to the fourth is cubed, giving me x to the 12th. And y is cubed, so y cubed. How can we simplify from here? Well, I have two of these y's, so two factors that have the same base. I can go ahead and combine the exponents. So x to the 12th, y to the 6 plus 3 is 9. Okay, if you got confused on that example, remember that we have here 6 y's multiplying themselves and 3 y's multiplying themselves. So how many y's would we have altogether? We'd have 9 of them. Here I have 2x over 5 to the third power. So 2 is cubed, x is cubed, and 5 is cubed. 2 cubed, x cubed over 5 cubed. 2 cubed is 8. X cubed over 5 cubed is going to give me 125. In summary, we have all these rules for exponents. It'd be good for you to write these exponent rules out. You might even consider writing each rule on a card and then an example on the back to quiz yourself. Test your understanding of exponent rules by simplifying the expressions. Assume that all variables represent non-zero numbers. Take a few minutes to try these problems, and then you can click to see the answers. How did you do? Let your teacher know if you need any more assistance on these rules before you move on to the next section.